when the elements was discovered, then its name was given on the name of its discoverer or on the basis of its property. So now what happens after a certain time, that is when the elements start discovering that, suppose one element is discovered, then every country start working on means the majority of the countries start working on the discovery of the next element. They start working on the discovery of next element. So what happens, that sometime it was observed that the two or more than two countries comes together the same element. So when the country comes with together with the same element, then different countries gives that different name to the same element, and that creates a problem. For example, there was an element whose atomic number is 4. Atomic number 4. This element was discovered by the two countries at the same time. The one is America, that is USA, and the second was Soviet, that is Russia. The two elements discovered, the two different countries discovered the same element at the same time. USA, when discovered it, it called it as a Rutherfordium. Rutherfordium, and represented by, that is a symbol RF. And when the Soviet discovered this element, the element having an atomic number 104, he called it as Kurchatovium, and write the symbol Ku. So when the element was on the country level, that is on their country level, the USA always called it as a Rutherfordium and the Soviet called it as a Kurchatovium. The problem arises when the same element comes to the universal level. So the problem was that what name should be considered for that particular element, whether it should be Rutherfordium or Kurchatovium. So such problems cannot be created in future. That's why the IUPAC gives a rule, it gives a nomenclature rule, so that whatever the next element will be discovered, they are going to be named according to the IUPAC nomenclature. Currently now the element having atomic number 104, the IUPAC select this name, that is Rutherfordium. So now in a periodic table we have this element with the name of Rutherfordium. But as I said, such problems should not create in a future. That's why the IUPAC gives a guideline for naming of an element. Now, according to IUPAC, what will be the name of this element? The name of an element having an atomic number greater than 100. We are talking about the element having a greater than, we are talking about the nomenclature of only those elements whose atomic number is greater than 100. The reason, because all the elements which are having the atomic number less than 100, they already have some specific name. So now what would be the name of this element? It totally depends upon, according to the IUPAC, it totally depends upon the digits which are present in the atomic number of the element. Like what will be the name? It depends upon the digit 1, 0 and 4. Every digit have some particular name, and with the help of name we make the name of that particular element. For example, let's see what is the name given for each digits. Suppose if there is a element 1, if the digit is 0, then IUPAC says to use a term nil. If the digit is 1, then use un. If it is a 2, use a term bi. If it is 3, then tri. If it is 4, then we use a term quad. If it is 5, we use a term pent. If it is 6, we use a term hex. If it is 7, it's a sept. And if it is 8, it's a oct. And if it is 9, then we have a term n. And similarly, we have a symbol for every digit. For example, suppose if now, once the naming is done, the next question is what will be the symbol that particular element. Then for the symbol, again, what will be the symbol of a particular element having atomic number greater than 100? It depends upon the digits only. Every digit, the first letter of the name is considered. This is called as a root name for particular digit. So first letter is considered as the symbol for the particular digit. Means if there is a 0, the first letter is N. So the symbol will be N. First letter is U, B. Here the first letter is T, then Q. For this it is P. For this it is H. For this it is S, O. And for this it is E. See, in the case of this since the symbol should be different for every element, that's why the no two elements have the first letter same in while in this root name. Generally, when it is a 9, we use the word known, but instead of known here it is used as a n. The reason because n is already used. Here if it is a 7, then generally we use a term hept, but here we used a sept. The reason because already h was present in number 6. Here generally if it is a 4, we use a term tetra, but here we use a quad. The reason because t was already there. So these are the names, or these are the words which we are going to use for a particular digit from 1 to 9. So if I'm using the same rule for the atomic number 104, so rule, what will be the rule, what will be the name of it? So for 104, so if I have an element with atomic number 104, then what will be the name? 1, that is un, 0, that is nil, and 4, that is quad. And the IUPAC nomenclature says that after writing all the root name for a particular digits, the name will have a suffix, that is IUM. So this element having atomic number 104 will have a IUPAC name as a unnil quadium. And unnil quadium, what will be its symbol? Then for 1, the first letter is U. Then for 0, it is N. And for 4, it is Q. So this will be the symbol. While writing a symbol, the IUPAC rule says that the first letter of the symbol should be capital and others are small in letter. Similarly, suppose if I am having an element 115, atomic number 115, then what will be its name? Then simply 115, again I will say it is un. Second digit is also 1, so it is again un. Then 5, for 5 we have a term pent, so pent. And finally I have to use a suffix IUM. That is, the name will be unpentium. Then symbol, the first letter is U, then second is U, and then 5, that is P. This is the symbol. Similarly, if I have an element like 120, what will be its name? So if it is 120, then un, then 2, it is by, this is 0, that is nil, and the suffix IUM. So the symbol will be UB, and for this is N, that is unbinilium. So this is the way how we named it. Let's see some more example, like 118 if I have. So the name will be un 8, that is oct. Suffix will be IUM. So octium it will be. The name symbol will be UUO. So on the basis of this, we can name all the elements having atomic number 101 to 10999, that is 999. Until now, the periodic table contains only 118 elements. So 104 unnil quadium, 105 if there is a 105, then it will be unnil pentium. If it is 106, I will call it as a unnil hexium. If it is 107, unnil heptium, like that. Again, there is some extra more rules, like if there is an element having atomic number 112, then what will be its name? 112, then it is going to be un. Second one is again un. It is 2, that is bi. And after bi, if I'm using a term, it will be IUM. That is, the name will be unbium. So here you can see that bi, there is a 2 I comes together. So in that case, the IUPAC says that remove one I, that is drop one I from here. So the name, instead of unbium, it will be written like this, un. After 2, you have to consider only one I, UM. So if before IUM, if again there is a one more I, before IUM there is a one more I, then in that case you have to remove one I. And this will happen only when the unit place contain 2 elements, that is 2 or 3, because there is only 2 elements, 2 and 3, which ends with I. So the IUPAC rule says that if 2 and 3 comes at a unit place, then in that case the 2 I will come together, so that one I should be dropped. So similarly, if I am writing atomic number 123, what will be its name? So it will be un. Okay, the symbol for this U and bi, that is B. This will be un bi, tri, and then one again IUM, so we have to drop one I, so it will be this. Symbol will be UBT, that is un-bi-trium. If there is an element, suppose having an atomic number 190, suppose if it is discovered in a future with an element with the atomic number 190, then what will be its name? So it is going to be 9 it is, so n, and 0 is nil, and then IUM. Now in this case again the scientists have some problem, the IUPAC says that if the 9 and 0 comes together, that is 9 and then 0, if the 9 is followed by 0, then in that case 3n comes together. 2n of is n, that is 9, and 1 is of 0. So in that case, out of 3, 1 n should be dropped. So now this will not be the name. The new name, the actual name is unnelium, and it is going to be U, and symbol will be U, not N, U, E, and N. So this will be the name of the atomic number 190. So these are the rules. If 112 or 113, we have this 2 and 3 comes at a unit place, we have some special rule for it, this, and the next one is 190. This will be either 190, 290, 390, 490, because only in case of 90 this rule will be applicable where the 9 is followed by the 0. So this is about the IUPAC nomenclature of the element having atomic number greater than 100. Now let's talk about the next is a prediction of the position, prediction of the position of the element in a periodic table. Suppose I know that this full periodic table contains 118 elements, and all 118 elements has been discovered. So suppose if a particular element is given and the question is asked that what will be the position of the element in a periodic table. So if I know the writing of electronic configuration, the proper way of writing electronic configuration in terms of sp, d and f orbital, then we can simply predict the position of an element in a periodic table. Now let's see how to write the position of a periodic table. Let's start with the first element, that is sodium. Sodium, I just wanted to write the position of this sodium in a periodic table. Sodium, whose atomic number is 11. Its electronic configuration is, it is 1s2, 2s2, to p6, and then 3s1. I have to write its electronic configuration. So for writing electronic configuration, we generally write three things. The one we mentioned block, means element will belong to which block. Then we write period or group, and then finally we write its period, in which period the element will belong. So to know the position of the sodium in a periodic table, we have to write all three things. So let's start with the block. I said in the earlier, that is, we have four blocks, S, P, D and F. How to know where element belongs to S block, P block, D block or F block? Then I simply say if the last electron enters in S orbital, it will be S block. If the last electron enters in P orbital, then it will be P block element. D orbital, then it is going to be D block. And if it enters in F orbital, then it is going to be F block. So if you wanted to know that sodium belongs to which block, then simply just see that the last electron of sodium enters in which orbitals. So here when I am writing the last electron, there is 11th electron. It is entering in S orbital, and since it enters in S orbital, so sodium is a S block element. S block element means it is a fixed, that is sodium is going to be 1, 2, 3, that is 7 and 6. These sodium will be one of the element out of these 13 elements. But still there are 13 elements. So for next I will write the group. Sodium belongs to which group? So So here I can say it's a S1. For a group, it will be better you write as it's a S1 configuration. S1 configuration means here, in the case of this here, for S, I said there will be two possibility. Either electrons will enter in a S1 orbital or it will enter in S2 orbital. So if the last electron is making a configuration S1, S1 means it will be here, and if it is S2, then it will be here. Similarly, for the D or for the P, there is a six possibility for the P. Either if the last electron enters in P orbital, then either it is going to be P1, P2, P3, P4, P5 and P6. These are the six possibilities. So if the last electron or if an element is a P block element and the last electron is making a configuration P1, then it will belong to the first group of P block. If elements enters to P2, P2. If elements making a P3 configuration, then it will belong to this P4. Similarly, P5 and P6. So all the element which belongs to this group, that is group number 13, they all have P1 configuration. All the element in this group, they have P2, here P3, P4, P5 and P6. Similarly, we have for D also. For D, it is D1. If electron is from the D block and it is having a D1 configuration, then it will belong to this first group of D. If it is having D2 configuration, then it will belong to the second group of D. D3 then third group, D4 then fourth group, and similarly I can say D10 up to D10. So here we are talking about the group. So S block, it's a fix. The element S1 configuration means the element is belonging to the first group of S block element, and the first group of S block element is a first group of periodic table also. So the group is first. Now about the period. Electron is entering to the element. Now at least I come to know that element is going to be in this group only. But still there are 7 elements. Now which elements is a sodium? Where is a sodium actually in this case? So that where the sodium is, it will be decided by the period. Now period is represented by, as I said in the talking about the modern periodic table, I said that here the period represents the outermost shell. All the element belongs to third period, they have 3 shells. All the element belongs to fourth period, they have 4 shells. So element belonging to which period is totally depends upon the shells. So element belongs to which period, it is represented by the valence shell, which is the outermost shell. So here if I am saying the outermost shell, it is represented by the principal quantum number. Principal quantum number, that is these number 1, 2, 2, 3. So you just say highest principal quantum number. So here the principal quantum number are 1, 2, 2, 3. That is highest principal quantum number is 3. So the period is 3. That is, it is going to be third period. So now it says let's see where the sodium is in a periodic table. It belongs to S block, means I have to just concentrate in this much area. In S block also it belongs to the first group of periodic table, that is only here, and third period. Third period means here, that is sodium is belonging to this point. After sodium, the next vanadium, whose atomic number is 23. So if you wanted to know the position of vanadium, then simply I will say, first you write electronic configuration. Configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and vanadium it is 3d3. Again, to know the position we require 3 things. That is, the first one is a block. Second, I require group. And then third needed thing is period. So vanadium, block. Last electron enters in d orbital. So it is going to be d block element. The next is group. For the group, we are concentrating on first you find out that since it being a d block element, which group the vanadium is present in which group of D block. Which group of D block means vanadium is having a D3 configuration, and if it is having a D3 configuration, that means it belongs to third group of D block. Third group of D block means here, but here we do not have to. Suppose if I'm like third group of D block, so third group is not the answer, because third group is a what? it is of D block, and I have to write the group of periodic table, in which group it is present in a periodic table. So periodic table group start with the S block. If you're talking about D3, means element is somewhere present here, then if I will start the counting of a group from the left hand side. So first when I will count, there will be a, okay, let's see, it's a third group of D block, but the periodic table never start with a D block, it always start with the S block. So third, and before this D block there will be a S block. How many groups of S block? Two groups. So total it is going to be fifth group. So here I can count also 1, 2, 3, 4, fifth. Then period. Which period? Represented by the valence shell. Valence shell, that is the highest principal quantum number. Highest principal quantum, like if I'm writing NS, then N stand for principal quantum number. So highest principal quantum numbers are 1, 2, 2, 3, 3, 4, 3. The highest principal quantum number is 4. So it belongs to fourth period. So let's see the position here. Fourth period means here D block, this area, in this also D3 there are 4 elements, and fourth period means this is the fourth period, means the vanadium is present here. The next is arsenic, whose atomic number is 33. So to know the position, I require block, group and period, which depends upon electronic configuration. So let's see the electronic configuration for arsenic. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p3. This is the electronic configuration for arsenic. So again the same thing, block first. Last electron enters in p orbital, so it is going to be a p block element. That means this element belongs from group number, from somewhere group number 13 to group number 18. That means in this region. Then for group, it belongs to third group of p block element. So third group of p block element, but periodic table, I have to write the number of group of periodic table, and the periodic table never start with the p block. So I have to start from this here, from the beginning. So first, see, always keep in mind that if such questions are coming in the exam, then the periodic table is never provided. So simply if I wanted to know the exact number of group, then we have to use the same logic which I am saying, that the group start with S block. S block, how many periods? 2. It belongs to P block. After S, there will be a D block. How many? 10. And then P comes. So if you are counting, then you have to cross the 2 groups of S block, then the 10 groups of D block, and then P block we are getting P block. So total number of group, I can say 10 plus 2 plus 3, that is 15th group. And if you will count here, the P3 will come at a 15th group. Then period. Highest principal quantum number, again I will say, the highest principal quantum number is, let's see the principal quantum, 1, 2, 2, 3, 3, 4, 4, 3, 4. That is a fourth. So period number is fourth. So it belongs to fourth period. So here it belongs to P block. In P block it is 15th group, that is P3 here, and that too in fourth group, that is somewhere here. One more example, that is chromium. The writing a correct electronic configuration is very necessary for knowing the exact position of the elements in a periodic table. Or let's say zirconium, or zirconium or lead, atomic number is 82. Configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 6s2, 5s2, 4d10, 5p6, then 6s2, 4f14. 4f14. Let's see how many electrons are covered. 2, 2, 4 plus 6, 10, 12, 18, 20, 20, 30, 36, 38, 48, 54, 56, and then 70. 10 more, that means it is going to be 5d10 and then 6p2. 70 plus 10 is 80, 80 plus 2 is 82. So now the position, p block element, last electron enters in p orbital, so p block. In p block, it is in a second group. So the number of group, it is going to be, I will start with the s block, that s ka 2, then p block, s after s d, and then p comes. So s2, d10, and then it is belonging to the second group of p. So the total group from the left hand side, it is 10, 14th group. And then period, then I will say simply the highest principal quantum number is 6. That means it is belonging to 6th period. 6th period, p block element, and in p block 2. That means this is the position of lead, that is pb in a periodic table. So this is about the how to know the position of a periodic table, position of an element in a periodic table on the basis of the electronic configuration.